next speaker is the program a few days ago was featuring someone who was part of the 18 cancellations that yours truly had to deal with to put the program together. So I think that at the end of the day, still the program became pretty solid. But what can you do without friends? And what can you do without a friend like Dan Stanzione, who will help us surviving the AI industry boom? So raise the hands if you never heard about Dan Stanzione. So your fame precedes you, my friend. and I really want to acknowledge how he just stand up to fill this slot. I know that he travels the world with slides, but still you need to put them together in a way that makes sense. And I asked him to be a little bit of bridging industry science.
Yeah.
And then we came up with this title. So, and the idea is that it becomes as interactive as possible as usual.
Thank you, Nicholas. Thank you for the yesterday 3 p.m. invitation to give a talk. So this is polished and prepared, as per always. You might remember last year, Nicholas said, the room's going to be full if everybody, I can't grow the conference unless people would come if I didn't invite them to give a talk. Would anybody come to New Zealand even if I didn't invite them to give a talk? And I said, yes, I would. And then he talked about how many cancellations he had on Monday. And so I sort of assumed this moment was coming. But, and yes, and he did ask me to be extra provocative. And for those of you who know my default stance on that, extra, yeah, you'll see. But really, I have two things I want to talk about in the brief time I am allotted here. One is the standard talk, just a quick update on what we're doing at TAC and the NSF Leadership Computing Facility, because everybody asks. And second, the question Nicholas originally asked me to answer in this talk is industry leading us to the right future? To which I said, well, the answer to that is obviously no. So what do we want to really talk about, but sort of how do we survive it moving forward? Because we've always had to sort of adapt to what industry wants to do. It's not a new question. So, but it's in an extreme state, I would argue. So, given the time, let's dive in on part one here. So most of you know about TAC, and I'm going to breeze through this, hopefully. So, but we're the University of Texas Computing Facility. We're the University of Texas System Research Computing Facility. But we're also funded by the federal government to be a national computing center, and that's where about 80% of the funding comes from, 90% with the other contracts. We also work with a number of other federal agencies when they exist in the United States. I think most of them are around at the moment. So no Homeland Security on there. We have about 200 people. We put up a whole bunch of servers. I actually, for another talk, was just working on our injection rate this morning. Jess has been watching me manipulate queues all week because we're building a lot bigger systems, but just our 4 existing big compute platforms right now, we get about 477 jobs an hour, or 8 every minute, from users around the world, several tens of thousands. So the queues are always new and different, and there's always something to fix. But yeah, so I've done some analysis recently, and there's a pretty big correlation between whether or not you receive grant funding and whether or not you use TAC, which is what I use often for my local users. But at UT, if you have an NSF grant, 70% likely you're a TAC user. If you have an NIH, so that's sort of the general science agency in the US, the NIH, the health agency, more than 50% of grant recipients are TAC users. But at any given time, we have users from about 400 institutions. We support about 3,000 different projects or allocations or PIs in a given year. This is actually our 25th year. June 1st is 25 years of TAC. We'll hit 125,000 users by then. Probably more than 100,000 of them have been grad students. So I think we've had a fair number of the grad students who are computationally literate have touched our systems at one point or another. Although, when you look at that 3,000 PIs, we have a few dozen PIs who've been around for all 25 years, and it's the same names every year, who seem to create the same problems every year. But about, in any given year, we have about 15 or 20,000 new users of the active. So, given how many are grad students, like 30% of the active accounts turn over every year. So most of the users are new at this, always, and they don't get better over time, which is something I have to keep explaining to staff, is that just because you taught them that 5 years ago, none of those people are here anymore. They're not going to remember. So, and again, we've supported many Gordon Bell users, 4 Nobel Prizes, and there's various programs that we basically give out time through to our various users. One of the great things about our job, my job in the US and what TAC does, is we are the underlying hardware and infrastructure for a whole bunch of the computational science achievements you hear about. So, you know, from stuff people you've heard from this week presenting here. And by the way, I appreciate you being the hardcore multi-core world attendees who are still here on Thursday afternoon and not enjoying the beautiful day and New Zealand scenery. But, you know, we're partners with the Odin Institute, as Karen mentioned, so all of the work that Karen presented happens on our system, and an Omar Gatasis 2025 Gordon Bell Prize, although the big runs happened at Lawrence Livermore. For that, we were longtime partners with DK Panda. We've been supporting the MVAPICH, MPI communication library development for the last 20 years, and are committed to doing it through the life of the leadership facility, but also in his new center, the iCycle, AI for cyber infrastructure and AI ag. All the APIs are developed by Joe Stubbs and his team at TAC. We're the underlying resources behind Ava Dielman's Pegasus and Swarm stuff runs on there. She mentioned some of the workflows that run on Frontera. Ilkay and Manisha's NDP, some of the infrastructure for that runs on TAC. It also uses APIs that we built. Right now, among the first non-hyperscaler customers for the NVL4 version of the Blackwell platform with NVIDIA, that's the new hardware we're bringing up. It's also the stuff Satoshi is bringing up. We have an MOU working together on some of that, along with NERSC. The United States is coming up on Vera Rubin shortly. We run a bunch of machines now. We have a bunch more coming to sort of tee up later in the talk in the next panel. We've been running at about peak power of about 9.5 megawatts, mean draw of a little over 6 megawatts for the TAC data center. We're building an additional 15 megawatts on top of that. The new machine is going to be about 13 megawatts. We have historically been CPU heavy, but if you go through the years, Frontera was 2019, really looking forward to turning that off. Actually, the compute nodes still do great. Really looking forward to turning off the 6,000 hard drives that make up the file system that fail. There went another one. Pretty frequent wait at this point. So that was 2019, was pretty CPU heavy. Lone Star 6, a little more balanced, 2021. Stampede 3 was 2024, and Vista is sort of our bridge to the new system where we switched to ARM, and now we have an all ARM, all Blackwell sort of system coming forward. So, and then a bunch of other various kinds of platforms, but we're going to add another 13 megawatts-ish to our load on top of the existing load in the next couple of months, actually. In this new building that just got finished, so our sort of big initiative right now is the NSF leadership class computing facility. They stuck the class in there so that Oak Ridge wouldn't be mad. Since Oak Ridge and Argonne claim the leadership computing facility mantle in the DOE space. But part of this, of course, is to replace Frontera and the aging machines in the fleet right now with newer, better computation. But it's also a real pivot for the NSF in how they're funding. Great headlines popping up on my machine. How they fund computing and cyber infrastructure in general from a sort of system by system. Every 4 years, all the centers compete. Some get new machines, some machines retire. You may or may not be working with the same people a couple of years down the road to sort of multi-decade long committed investments in having machines in place, which really makes a lot of sense for the big science instruments. There was an SKA talk earlier in the week. You've seen the timescales for that. We're actually working with the US equivalent, the Next Gen Very Large Array. Last year we did a big planning exercise with them, but they probably won't start construction until 2028 and take first data until 2032. They won't hit their full data rate until 2039, and they're going to have data running through 2051. Telling them I have a machine for 4 years that might disappear and then nothing is there anymore is not really good when you're doing the risk management review for $1 billion project, right? So you need a computing partner that exists on that time scale. So the hardware is still going to wear out at the usual rate. NSF's committed to operate the facility for 10 years with a 10-year renewal. At some point, somebody might bid to operate it other than us, but we'll have a 10-year, that's a 2036 problem. I don't really have any 2036 problems. But the idea is that the machines and the facility will be there even as the hardware is replaced and the operator is replaced. There will always be, now through 2046, a leadership class computing facility. So it's a long-term investment to match the long-term missions that we support. So this project, after many years of planning and various congressional gateways to get through and surviving budgets, I did push really, really hard to get it started before the current administration came in. So we started July of 2024. We're about a year and a half into the construction phase. The data center is built. I'll show you a picture on the floor in a second. Commissioning should actually finish tomorrow. Tomorrow here, 2 days in the States. Sorry, not in this building, but we've deployed in our existing data center the new archive system. It is an exabyte, designed for exabytes from the ground up for tape archive. It's the latest iteration of Ranch. We've always called the archive Ranch. It's where your data goes to retire and hang out. So we have continued the trend going back now. There's actually been a continuous tape archive we've had in production at UT since 1986. So good luck reading most of the 1986 files if they're not text. But we do have files from 1986 on here. So more than 40 years of continuity on this. Amazon does not have that because they didn't exist then, or Google. But as per always, the new data is 90% of the data. So people ask, what's our retention policy? How do we purge files off Ranch? I just don't. Because the old Ranch was 100 petabytes. The new one's an exabyte. The one before that was 10 petabytes. The one in 2006 was 1 petabyte. So at most, 0.1% of my capacity is all of history through 2006, right? So 90% of the investment is always the new data, and 10% is all of history. And as long as that trend of digital data continues, 90% of all data generated by humanity is in the last 3 years, always. So as long as that trend continues, we'll keep all the data on Ranch. So that's done. We have several tens of petabytes that have migrated over. Tape migration's a long, long process. So we have another year on the other one. Horizon is the machine that's coming in. It'll have 2,000 GPU nodes that are Grace Blackwell GB200, so 4,000 GPUs. Later this year, we'll add 5,000 Vera-based CPU nodes, so the next generation of NVIDIA ARM will come out to around 1 million cores when that happens. I have no idea how to measure compute performance anymore, even though it used to be what we did for a living. So you can pick your number. If you like double precision and you believe in matrix multiply as part of double precision and not vector operations, it's sort of arguably 300 petaflops. It'd be 600 if you include emulation, and it'd be 600 petaflops. If you believe in Int4 TF4 for all of our AI apps, it's 80 exaflops. Yeah, you could argue for real vector double precision FP64, it's more like 200 petaflops. Pick your favorite number. There's a 500 to 1 range now. I think we might submit like 7 top 500 numbers before it's over for the machine. So we're using the new Dell Rainwater integrated rack infrastructure. We'll have a fully solid state file system at 400 petabytes, which has gotten interesting in recent years with pricing, and a 16 terabyte per second read speed on that. 8 terabyte per second write speed, which is the hard part. We've been telegraphing this migration for years for us to a more GPU-centric and ARM-based system. So we did Vista a couple of years ago. Dell never built a Grace Hopper or Grace platform, even though I told them years ago that maybe you should align closer with NVIDIA. They might turn out to be something kind of big. But Dell didn't do that, so we brought those nodes from Gigabyte along the way. If you'd like to have long conversations about the service level that Gigabyte can provide, I'm happy to trash them in public or private forums at this point. But we did 600 Grace Hopper nodes, a couple hundred Grace nodes. Our basic calculus on this, which has so far turned out to be right after 18 months of production, and as of today, 583,000 jobs on this machine, is that we would much rather port the entire scientific software stack to ARM, following the steps of Fugaku and many other things that have moved to ARM, whole Apple ecosystem, et cetera, than try and port the AI stacks away from NVIDIA to somebody else's GPU. I still feel good about that 3 years after that decision, but we've had a very smooth migration. So Horizon, again, happening now. Frontera, the system it's replacing that was 40 petaflops, was about 6 megawatts. This will be more than double. Building utilities quickly on campus got to be a problem. So this new data center, which is right down the street from Dell, it's in the direction that the picture was taken from, but another 200 yards is the Dell campus in this direction. It turns out it's right across the highway where the Austin energy monopoly ends, and you get onto the deregulated part of the Texas power grid. And SABE already had an 85 megawatt substation shown in the back built out there, and that was key. Because to add power on campus, I needed a 5-year lead time, and I had to prepay for the transformers to bring in the additional power capacity we would need. I love people who think they can get a gigawatt in a year, but the 4.5 years to get the transformers if I gave them $8 million ahead of time. So we partnered with SABE. We ended up using about half the power they had meant for the building, even though in floor space we're only using about a quarter of it. But it's been great, and we're ready to deploy racks. This was sort of the state in September. Everything is obviously liquid-cooled at this point, so you build in all the underfloor piping, et cetera. That's for the primary loop. There's a secondary propylene glycol loop. By October, we had raised floor. More recently, we've had load banks tied into the busways and the piping to do the full 15 megawatt commissioning testing, actually 16 megawatts commissioning testing. Those should be getting pulled off the floor starting today, I hope. So, but let me say a little bit about the racks, because the physical challenges have been pretty substantial. And again, a few things I want to say a little later about the supply chain and are influenced by this. But we're using the NVL4 Blackwell. The standard NVL72 configuration, you get 72 GPUs in a rack. Because we're not wasting half the rack on NVL switching, we're putting 144 GPUs in a rack, shorter cables, better latency. But that means with the rear door attached, it weighs a little over 6,000 pounds, so call it 2,800 kilograms per rack. That's 2 Honda Civics, depending on which set of option trim packages you get on your Honda Civic. If you got 2 electric sedans, you'd probably have about 120 kilowatt hours of battery. So you could take your electric car and drive it 500 miles on 2 charges, or you could run the rack for 28 minutes. So we'll come in, we're planning 225. I think we'll land at about 215 kilowatts per cabinet in this space. Roughly the same form factor for the CPU racks, but they'll only be about 100 kilowatts per cabinet, and hopefully a little under the 6 tons, but or 3 tons rather. So it's a lot. And yeah, one of the learnings from this is the first rack that Dell shipped, not to us, fortunately, but to a DOE lab in this form factor. They put it on a standard pallet and bolted it down, and the pallet collapsed and it bent all the bolts, so they couldn't get it off the pallet. So now we have new composite pallets. You can't use a wooden shipping pallet anymore for racks. Turns out we had built a 6,000-pound floor that can handle it, but nobody thought about the ramp. So we're forklifting them up onto the floor because you can't roll them up the ramp without it collapsing. So there's substantial pieces of infrastructure here. I was hoping, this story is no longer true, and I'll show you why in a minute, but for me, I got my first personal hard drive in 1985, and I was hoping 2025 was my last one for spinning hard drives. It was a great technology. I was excited about it then. I'm excited to see them go now, but the primary Horizon storage, this is still true, is all solid state. So from a bandwidth perspective, we're going to have about 25 times what we had on the last machine because we wanted to invest more heavily in I/O, given how many workloads are I/O limited. We saw that even in some of this morning's talks. Given that it's all solid state and we're moving away from Lustre, I think for the small file access patterns we see really all the time, but particularly in the AI workloads, we have this myth that big, good parallel I/O is, large stripes that end up in giant files, yet most of the IOPS are like 4K in reality. But certainly with AI, we see a lot of sort of what seems like random access. So we think we'll see better than the 25x. The primary systems, the Scratch, the home, all the stuff directly connected is vast. We've been using that on Vista and on Stampede 3. We've been pretty excited about how hands-off it is. But we've also been building out some Vidura and Weka, name for the bird here, I guess, deployments from other parts of TAC for the Kubernetes storage and some of our deeper storage. I'll talk about why when we get to pricing. So this is the state of things in January. We are actually in the process of deploying. That's 140 pallets of really expensive SSDs that I resisted the urge to flip on eBay, given what's happened to SSD pricing, where it was going up 20% a week in December and January. And it's like, well, it was $10 million 2 weeks ago. Two compoundings, it's $16 million now. Okay, but anyway, they don't let you stack them, so hence the little cones. These have all been built into, plus pallets and switches and empty cabinets for building all this out. That's the built-out storage racks that we're still waiting on GPU racks. In fact, the first one built just failed commissioning, and so it's being rebuilt right now. I've learned many definitions of the word next week since last October for when those will get delivered. So, and just to transition to the last part here, we're of course getting crushed by market pricing in this space, as all of us are, right? So I got this chart from Ken Claffey at Vidura, and so this is showing just pricing of SSDs and hard drives for the last 12 months, right? And so if you just start with like conventional hard drives, mechanical, relatively easy to ramp production, the story's not good, right? Per bit, you're paying 60% more than we did last year. But if you look at the startling flash drive prices, last year I could make the argument that it's only 5x more to put things in QLC flash than it was for hard drives. And frankly, with all the dedupe and compression and stuff, you can do so much easier with an SSD than a hard drive. For collating duplicate blocks, et cetera, really it was like 2.5 times the cost. 12 months later, it's 15 times the cost, even though hard drives are more expensive because our flash drive prices for a 30 terabyte SSD has gone from $3,000 to $13,000 in 12 months. Because most things in technology, Moore's law is everything doubles in price every 4 months, right? So, prices went down from 1947 until 2023, and then the trend has reversed in the last 2 years because of the crazy demand. And it's not just SSD, right? DRAM, similar story. One problem with SSD is if you look at what like Micron can build and you realize how much Microsoft has ordered, and you understand that that's more than Micron can build in 2 years in outstanding orders, you see why the prices are going up. But GPU prices are also through the roof, right? And so, those Blackwell nodes, the Grace Blackwell board, it's about as much as a Rivian pickup truck, right? The electric truck. I think the list on it is $140,000, $150,000, right? $60,000, $70,000 a GPU. We're paying less, but still $60K is a decent street price for a Blackwell at this point. For 20 years, our sort of inflation-adjusted real price per nodes from Ranger, the Stampede systems, Frontera, $6,000, $8,000 a node, right? Do an 8,000 node system for $60 million with storage, with network, right? Modern Blackwell multi-GPU node, $120,000 a node. If you run systems, your user experience is very, very different if you give them 150 nodes to run on versus if you give them like 8 or 2, right? Especially since scientific users really love to share. Memory, bandwidth, all that stuff, right? We've had to, with some VMs and stuff like that, change the way we manage. We'll have 2,000 Blackwell nodes. We had 8,000 CPU nodes. The machine costs more than twice as much, more than 3 times as much, in fact. So we're seeing this convulsion in the markets around AI demand that have driven prices through the roof for things that are clearly not worth that much because you could buy them for a lot less 12 months ago, right? So, and of course, we now have the political pushback that's coming with this. Not too long ago, a New York Times article where now you can drive through rural America and find barns with "Say No to Data Center" signs in front of them, which was not a big thing in the last, until this year or the past year. I think investor pushback is what's ultimately going to make the difference, but there's some political pushback that seems to be growing around these things. So we have sort of soaring costs, and I don't want to get into the validity of AI for science because I think tons of cool things are going on, but it's undeniable that the sort of commercial application for AI has really changed the market dynamic we work in. Another sort of important but underestimated factor in this is the perils of the fact in how we finance all this stuff, or what's generally called the financialization of the world at this point. If you've seen the big new hot company is Kalshi, where you can trade anything as a decision, right? So let's just make the transaction, not the thing, where the money goes. There's an article I've cited here about the financialization of the world from the New York Times, but if you look back in time, there's a famous scene from Mary Poppins, took the kids' money and said, here's what we do with it. But once upon a time, banks took deposits from savers and then in turn loaned those out to companies who would do productive things, right, to try and efficiently allocate capital and to provide liquidity. And those companies bought ships and built buildings and did things that led to, for the most part, good jobs and improved living conditions. And that was the way the financial markets were intended to work. By most estimates, now that's about 4% of the financial industry is taking customer deposits and reloaning them out to productive business investment. It's 2% at Goldman Sachs, it's 4 or 5 at Morgan Stanley and JP Morgan, the sort of big ones. But the rest is basically vampirism in the financial industry. Is this controversial enough? Sucks the life out of stuff. But 90 to 95% of the business by dollars is debt refinancing, balance sheet restructuring, mergers and acquisitions. If you look at the amount that the financial sector is putting into investment in companies as a percent of GDP and new companies and business growth, it's less than half of what it was in the 1960s. If you look at their profits, it's orders of magnitude higher than it was in the 1960s. And the financial industry takes 25% of all corporate profit in the world goes to the financial industry, right? So to invest much less in companies and to mostly do things like charge fees for refinancing your debt. Which clearly creates jobs, right? So refinancing debt. So in the financialized world, businesses, by the way, Oracle's borrowing $180 billion from these guys right now to build AI data centers. Businesses are entities for cash extraction, not for creating jobs, not for creating goods, not for improving the world. Hence, you end up with nursing homes who are acquired in leveraged buyouts and have billions of dollars in debt. In the business that we all thought would be the one where we make the most money, caring for old people before they die. So this is sort of our backdrop for investment in AI. So nobody's paying for this AI boom in cash, right? Microsoft spent about $80 billion of their own cash, but they're the only one who had that kind of cash. So if you look at various estimates, I can throw in some references, but since I made this slide 3 hours ago, I didn't, but the estimate of the money spent so far by the big players on data center infrastructure and equipment is $815 billion, right? So roughly the US Defense Department budget. So the estimated spending for this year is an additional $600 billion, right? And by the way, this is not in roads and bridges and stuff that last 50 years. It's in computers that last 4 years on a good day. And what's in place appears to be, the estimates are all over the map, but 100 gigawatts of power, which is about 23 times New Zealand's, right, entire power grid, is what's existing in data centers today. McKinsey's forecast for the mid-range growth scenario for AI for 2030 is that it would hit 559 gigawatts of data center power. That's 47% of the entire United States' power, electrical capacity today. Right, so, which is a substantial fraction of the world's. So, because we waste power like no one else alive. But anyway, so some ask, is this a bubble? To which the answer is obviously yes, right? There's not even, I don't know why it's a debate, right? So let's just do some rough math on this. This is as technical as this is going to get. If you have a $1.4 trillion in capital investment by the end of 2026, what's the interest on that money, right? If you're a really good company, AAA rated, you can borrow money at about 5%. If you're taking money from venture capitalists, they like to return 10 to 12%. Or if you're doing B-rated bonds, let's just say 7%. So for what's already been spent, they need to make $100 billion a year on AI product to pay the interest, the break-even point on the interest on the money. If you're only at 100 gigawatts of power now, I'm in Texas, I can get power pretty effectively, but to draw a megawatt for a year costs me about $600,000, the large corporate rate. So 100 gigawatts, call it 60 billion US dollars a year for the electric. If we get to 500 gigawatts by 2030, that's $300 billion a year for the electricity, right? just the electricity. This is not the traditional software model of how you make money when you have this sort of capital. 2/3 of that 1.2 trillion is the actual racks, the GPUs, the servers, and the storage, right? About 1/3 is the data centers themselves and the infrastructure and the land, and that lasts a little longer. But maybe 4 years is commercially viable. Who's doing production AI on Voltas 4 years ago, right? Not Amperes, not Hoppers, not Blackwells, Voltas. Yeah. So depreciation, now they're actually taking it for tax purposes over 6 years, which nobody believes, but it makes their balance sheets look better. But if you take a 4-year depreciation, that's $200 billion a year just for the IT gear. So if we use the low number for power and financing in that, break-even point on the infrastructure to run AI is $358 billion a year, growing to $600 billion a year by 2030. That's, so today it's only $1 billion a day to run the infrastructure. So that's just infrastructure. That assumes they don't pay any salaries or taxes. One of those things might be true. But there are people involved in this, right? There's no profit, there's no marketing, there's no anything else, right? That's just the base infrastructure cost to do AI. They have to make $1 billion a day. If Nathan's problems at Los Alamos National Lab cost a few $100s a week in tokens, and they're already paying for that, they're totally screwed. OpenAI's 2025 revenue, including their deal with Los Alamos, $10 billion. Their data center obligations over the next 5 years, $1.3 trillion. Right? So yes, this is a bubble. This is what a bubble looks like. When you can buy a product that is the exact same product 12 months later for 4 times the price, that is the definition of bubble. It's Cabbage Patch drives. You say, hey, at this point, it's pet rocks, but you don't get the rock. So like most bubbles, this one isn't the result of any sort of planning or careful growth or decisions that were made ahead of time. ChatGPT hit, and then everything exploded, right, in a few years. So demand hasn't been growing like at a healthy 10 or 15%. It's been growing at like 1,000%. The global server market is 5 times bigger than it was 4 years ago. It's just ridiculous, right? Orders for almost all the components exceed what there is global capacity to make. Some second-order effects of that are fun. Almost everything is running out as fast as they can force it out the door, right? Designs are fast, they're largely untested, quality control is terrible, marginal stuff that wouldn't be sold is getting sold. I see it all over the place, lots of vendors, lots of things, right? Again, our first GPU rack, they put it all up in their big exciting rack. Racks used to just be sheet metal, it was hard for them to fail. Something failed, they've torn it all out, they're rebuilding the rack. But everything is going out the door as fast as they can get it out the door. Nobody is optimizing for anything. Because it's get the chip, be selling it in 30 days, move it out as fast as you can. Get the drive, move it out as fast as you can. Everything's designed for the hyperscaler problems because they're the ones who spent $815 billion in the last 2 years on this. We didn't. The government spend is nowhere near that. The scientific computing spend, we're a tiny piece of this. By the way, that's on top. That was just the big commercial players' spend that needs $1 billion a day without our spend. So quick example of the ramifications of the way this gets designed. So the dominant design of the world, it's an older slide, but for pushing Blackwells out right now is the NVL72, right? 72 NVLink, it's the successor of the DGX. It's what NVIDIA has been pushing for rack scale infrastructure. That's the very simple picture of a node, the shelf in a node, which I think I've scrubbed most of the non-disclosure things off of at this point. But let's say this is a nameless typical NVL72 node that you could get from NVIDIA. If you start looking around, you have, let's count network interfaces. Here's a 1.8 terabyte per second NVLink connection. There's 4 of those, 1.8 terabytes per second, right? Here's a CX7 and 400 gig InfiniBand link, 2, 3, 4 of those, another 1.6 terabytes of bandwidth. Here's 2 Bluefield 3 cards, so that's 200 gig InfiniBand with a DPU to go to the storage network, but it has 200 gigs, you got 4 200 gig paths. Let's just call that 2, and then we have some fast management Ethernet over here to get out. Also, by the way, from Mellanox, adds, I don't know, $1.5 million per rack to the cost to put 11 network interfaces per node that run at 4 different speeds and latencies, and by the way, all talk to different sets of nodes, because the NVLink is just in the rack, the InfiniBand is multi-rack, the Ethernet's presumably global, the storage area network just goes to the storage. think about how you might set up libraries for the optimal routing of messages through this environment. By the way, there's also 6 physical memories in this node. So every Grace and every Blackwell has its own memory. It's unified memory architecture, but there's 6 physical memories. So if you want to do the optimal reduce, there's only 72 combinations of network and memory that you'd have to run through. And users really love that, right? In my experience, if you give the users Ethernet and InfiniBand, there's a 90% chance they're going to pick the wrong network. 2, Murphy's Law, and onto the 50-50, 90-10, they get it wrong when you're asking them to grab a Python container built correctly to run on that app. What happens when they have 11 networks and 6 memories to pick from, right? So the odds of anybody doing that well are roughly 0. So, but do we need 11 network interfaces? That's a ton of bandwidth. By the way, the difference between an NVL72 rack with 72 GPUs, the 144 GPU racks we're buying, we can get twice as many GPUs for about 25% more. And the reason is all the network here, right? So you're paying a huge premium to do this. So obviously all of your apps need it, right? Well, again, to grossly oversimplify and finish in under an hour, HPC apps really care about latency more than they care about bandwidth, right? We all know there's a million reasons that's wrong, but by and large, it's true 70% of the time, right? If you add 11 interfaces instead of 1, in the very best case, your latency is the same. It's probably worse, right? When you deal with channel bonding and picking interfaces, et cetera. Any logic adds latency, right? So it's not good for HPC apps. So obviously the AI workloads must have huge demand. So I went and found workloads running PyTorch training jobs for various kinds of models on Vista, and we started grabbing the network stats from them. And the average 64-node run, you see about 1.5 gigabytes per second, not terabytes per second, of network traffic per node to run at 64 GPUs. So it's way less than what one in IB Link could handle, right? We have way more bandwidth than that. They're just not demanding it. Certainly it's trivial compared to even one of those 4 NVLinks being connected. So why is it all there? Well, I talked to some people at NVIDIA, and they're like, you don't really see the demand on the NVLink till you hit runs of a few hundred nodes. So a few hundred $60,000 a piece GPUs is the minimum place where you start needing this network that they're building into every rack they sell, and it's like 40% of the total cost, right? So if your normal computer for your normal customer, for any of you, is a computer that costs, a few hundred 60K GPUs, you buy them a $20 million machine and you give one user the whole machine all the time, then maybe you need that network. And for everybody else, it's a waste of money. And it's the dominant design we're selling. It's where most of the racks are going out the door because no one is taking the time to think about any of this, right? So is this the correct solution for most of us? Is it even close? Does anyone care at the rate they're spending money? Interesting question. So there's risks for us now in this, right? One, yes, we're overpaying for everything, such as life. If you can wait till the bubble bursts, do so. I think the bigger problem is that when the bubble bursts, everything's going to get a lot cheaper, but the disillusionment and the associated global recession will paint with a very broad brush, and governments won't want to invest in computing anymore, even if it's the commercial AI that busts and nothing we do had anything to do with it, right? So this has actually been a pretty easy climate to get HPC government funding investments because you just say, you don't want to miss out on AI, do you? And then they add a 0 to your budget. And so, when that goes away and it's like, yes, we definitely don't want to invest in this right now, I think, we're at huge risk from that. But at the same time, there's a lot of productive things we can do to survive this. And I promise to wrap up shortly here. But I've been thinking, at one point that we had a data center that could handle 60 and 100 kilowatt racks, and now 250 kilowatt racks, and that we had 30 megawatts of data center would make us like one of the bigger and denser data centers in Texas. And now with Stargate at 9 gigawatts and the other 7 gigawatt one in Abilene and various ones, we're probably not in the top 50, right? It's just not a thing that differentiates us anymore. Commercial scales are unthinkably huge. I'll never have even a government investment if I had the whole DoD computing budget that will rival the scales of what the hyperscalers are going to spend, right? So in one sense, thinking about it from our perspective at TAC, right, we have more funding than we've ever had before. We have bigger and denser data centers than we used to, but we're now 1/300th the size of the largest ones. Do we just give up? right? And I would argue no, that there's things that we can absolutely do. And you have to think back to ancient history, though, like before ChatGPT came out. So you have to go back to like 2020, just infinitely far back into the past, right? So, but there was, in fact, this paper has come up in this conference this week, right? But Moore's law was ending. We needed to do something to improve computing performance. By the way, we'll get off the cheat of we've been doubling AI performance by going from 64 bits to 32 to 16 to 8 to 4. Two more generations of that tops, by the way, unless you think we can get to a half. But what does below 1 bit mean? But the notion was the plenty of room at the top paper that somebody showed. I've forgotten, but in an earlier talk, right? All that headroom is still there, right? Software optimization, things we do inefficiently, better ways to move data around a chip, et cetera, right? So I think we need us, but by us, I mostly mean our users, who if I tell them things like, on these GPUs, you're getting 32-bit is 64 times faster than 64-bit, they're going to figure out clever ways to exploit that. And we're seeing it all the time, right, of how we use, AI tricks and AI hardware to make the science go faster. So the two things we need to invest in, and frankly, neither of these is really new. They're just sort of extreme for now. Back to when we had to switch from vector machines to microprocessors, right? It was how do we take the machines that industry is definitely going to build, which right now is low precision, commercial AI-friendly hardware, right? That's what they're going to build. It's what the demand's for. There's nothing wrong with that. How do we make that work for science, right? How do we do emulation? Ozaki scheme on steroids, extending it past matrix multiply to the regular vector operations that make up a fair chunk of the codes, right? So we need to find clever ways to make int8 our way of operating, and we can, right? We were never going to get all the problems to work on microprocessors and commodity networks. Only a few would work. Remember the famous debate between Danny Hillis and Seymour Cray in the 80s was, if you needed to plow a field, because Cray was arguing vectors, Hillis was arguing clusters, and Cray said, look, if you want to plow a field, do you want to have 4 strong oxes or 1,000 tiny chickens to pull your plow? Turns out 1,000 chickens was the right answer, right? Which is kind of counterintuitive for plows, right? But we made clusters work. And maybe we're less efficient than vectors, but it works, right? But we need to do that again with the hardware we're going to get, which is going to be friendly for doing PyTorch, right? And then the other thing is, we know these AI workloads aren't using hardware well, right? The last talk was a lot of low-level, below CUDA level optimization of how to make waves work efficiently, right? Which very few people are doing. But you don't need $100 billion of infrastructure to answer these questions. You need a GPU or two, right? And you can figure this out. And there's huge opportunities for academia in addition to all of our usual things and how we do science and how we use AI for science. But these two things, I think, are going to define how we get through the bubble and after it. But this, finance is gravity. It's going to pull all this stuff down at some point. And the costs don't matter era of AI isn't going to last, right? So if you do this work, it matters now, but it's going to matter a lot more when people remember that there's a budget for stuff and that it might be finite. So that's your provocative comments for the day, Nicholas. So I'll stop there. Thanks.